Bismillah, Alhamdulillah, wassalatu wassalamu ala Rasulillah. This is the second part of section 11.7, and it's about the root test. The root test is similar to the ratio test, but we apply it when we have nth powers. Okay, we take the nth root of the absolute value of an. So, for example, this is series, and an is this. An is 2n plus 3 over 3n plus 2 to the power n. This is summation an and this is an. And now we take the nth root of the absolute value of an. So what is the nth root of the absolute value of an? Of course, this is n. Okay. And n, this n, cancels with this n because this is, you know that the nth root of a is a to the power 1 over n. So the nth root of a to the power n would be absolute value of a. Okay. And this is positive. N is greater than or equal to 1. So this would be equal to 2n plus 3 over 3n plus 2. So when we take the nth root of absolute value of an, we get rid of this n. So this is what we mean when we have nth power. This is an nth power. And now the test says find the limit of this amount, which is the nth root of absolute value of an when n goes to infinity. And you know we take the terms with the highest power, and the limit is 2 over 3. So 2 over 3 is L. So now we found the limit of square nth root of absolute value of an, and it is L. Now this L, if it is less than 1, the series is absolutely convergent. If it's greater than 1, the series is divergent. If it is 1, the test fails. Similar to the ratio test. This is less than 1. So by the root test, okay, summation an is absolutely convergent. Notice something here. If the limit is 1 in the root test, then the limit in the ratio test will be also equal to 1. So there is no need to try the root test if you have L equals 1 in the ratio test. And do not try the ratio test if you have L equals 1 in the root test. Try other tests in this case. Now determine whether this series converges or diverges. If you see that you have an n here and you want to try the root test, so the nth root of absolute value of an would be equal to n will cancels with n, and you will have n over n plus 1. And when you find limit when n goes to infinity of this amount, it is 1. Highest power over the highest power, the answer is 1. So test fails. Okay, root test fails. So I have to think of other tests. But if you take the limit of an, this is an, okay? If you take the limit of n over n plus 1 to the power n when n goes to infinity, we evaluated this limit in a previous video. If I divide by n in the numerator and the denominator, divide the denominator and the numerator by n, then this would be limit 1 to the power n, that's 1, and 1 plus 1 over n to the power n. So I can write it 1 over limit n goes to infinity, 1 plus 1 over n, and we have seen that this limit is equal to e in a previous video. So 1 over e is not equal to 0. I found the limit of an, the limit of an, and I found that the limit of an is not 0. So by test for divergence, if you remember, there is a test called test for divergence in 11.2. It says that if the limit of an is not 0 or does not exist, then the series is divergent. So by test for divergence, summation an is divergent. So we were not able to use the root test here, it fails, but we used the test for divergence to prove that this series is divergent. Please check section 7.2 if you remember, if you do not remember the test for divergence. Use the root test to determine whether the series is convergent or divergent. Okay, what is the nth root of absolute value of an? It is n squared plus 1 over 2n squared plus 1. Now let us find the limit of this. So what is the limit? When n approaches infinity, of n squared plus 1 over 2n squared plus 1. If you take the highest power, so it's 1 over 2. And 1 over 2 is less than 1. So by the root test, summation an is absolutely convergent. If we want to use the root test here, this is negative 1 to the power n minus 1. I can write it negative 1 to the power n times negative 1 to the power negative 1. But this is just 1 over negative 1, so it's just negative 1. If I take, okay, if I take absolute value, the nth root of absolute value of an, in fact, the absolute value will get rid of the negative sign. So I will have the nth root of, let me write it like this. I have negative 1 and negative 1 over ln n to the power n, okay, absolute value. So the negative will disappear, okay, and also this negative will disappear. I can take n outside. Let me write it step by step to show you that. Now this negative will disappear. So I'll have negative 1 over ln n still inside the absolute value to the power n. Okay. N will cancels with n. And now the absolute value of negative 1 over ln n would be 1 over ln n. And the limit of 1 over ln n when n goes to infinity, 1 over ln infinity, 1 over infinity, that's 0. And 0 is less than 1. Okay. You can write it in another way. You don't have to write it like this. I think this way seems you just can say that absolute value, if you want, absolute value of negative 1 to the power n minus 1 over ln n to the power n to the power n. Okay, equals absolute value of -1 to the power n minus 1 over absolute value of ln n to the power n, and this is 1 over ln n to the power n. That's it. And then you take the nth root of 1 over ln n to the power n, and this would be 1 over ln n. You can write it in any way you like. So here, by root test, summation an is absolutely convergent. Well, the nth root of absolute value of an is the nth root of absolute value of -2n, okay, over n plus 1 to the power 5n. I can take the power 5n here. N cancels with n, and I'll have absolute value of -2n over n plus 1 to the power 5. And now absolute value will remove the negative sign. So I'll have 2n over n plus 1 to the power 5. And now the limit when n goes to infinity of this quantity would be equal to, I can make or take the limit inside the power. That's acceptable. We studied the properties of limits in calculus 1. And now the limit of this when n goes to infinity, if you take the highest power, 2n over n, so 2, so the answer is 2 to the power 5. And 2 to the power 5 is 32, and that's greater than 1. So by the root test, summation an is divergent. I have n square here. So the nth root of absolute value of an would be the nth root of, there is no need of the absolute value here. This is 1 plus 1 over n to the power n square. So it is n. I can write it. Yeah, n to the power n, because n times n is n square. When we have a to the power m to the power n, we write it a to the power m times n. So now this n will be cancelled with this n, and I'll have 1 plus 1 over n to the power n. And now the limit of 1 plus 1 over n to the power n when n goes to infinity, we have seen that this limit is e, and e is greater than 1. So by the root test, summation an is divergent. The nth root of absolute value of tan inverse n to the power n, I can take n outside, n cancels with n, and I will have, when n starts from 0 to infinity, for n goes from 0 to infinity, tan inverse n is positive. This is the graph of tan inverse n. This is the line y equals pi over 2. and another horizontal asymptote y equals negative pi over 2. So from 0 to infinity, it is positive. This is tan inverse x. So n as a sequence would also lie on this function. The limit of tan inverse n when n goes to infinity is, as you can see in the graph, pi over 2, and pi is 3.14 approximately, around. If you divide by 2, this is a number greater than 1. Okay, it is 1.57. So pi over 2 is greater than 1. So by root test, summation an diverges or is divergent. Now use any test to determine whether the series is absolutely convergent, conditionally convergent, or divergent. I have n here, so I'll use the root test. When I take the nth power, notice something. If I replace n by 1, 1 minus 1 would be 0. If I replace n by 2, 1 minus 2 would be negative. So this is negative, while 2 plus 3n is always positive. So I will write it nth root of absolute value of 1 minus n over 2 plus 3n to the power n. N cancels n. But now the absolute value, I cannot remove the absolute value because 1 minus n is not positive. But in fact, for n greater than or equal to 1, for n greater than or equal to 1, 1 minus n is less than or equal to 0. If n is 1, it is 0. If n is 2, it is negative. If n is 3, it's negative. It's always negative. It's always less than or equal to 0. So I can write it negative 1 plus n over 2 plus 3n. You know, absolute value of x would be equal to negative x if x is less than 0. You can write equal, of course, less than or equal to 0. It's true also. So now limit negative 1 plus n over 2 plus 3n when n goes to infinity. If you take the highest power over the highest power, it is 1 over 3. And 1 over 3 is less than 1. So by the root test, summation an is absolutely convergent. Well, this n here has no power, power 1. So using the root test here, I'm not going to use it because I don't have power of an nth power like this. So I'm going to use the ratio test. To use the ratio test, I need to find an plus 1 over n in the absolute value. For the ratio test, you can check the previous video. Negative n to the power n plus 1, negative 9, over n plus 1 times 10 to the power n plus 1, so plus 2, divided by or multiplied by the reciprocal of an. And now some cancellation. This cancels with this, and I'll have negative 9 here. And this cancels with this, and I'll have 10 here. So this would be equal to absolute value of negative 9 is 9, so 9 over 10 times n over n plus 1. And the limit of 9 over 10 times n over n plus 1 when n goes to infinity, the limit of n over n plus 1 is 1 when n goes to infinity, so the answer is 9 over 10. And 9 over 10 is less than 1. So by the ratio test, summation an is absolutely convergent. I have nth power, so I'll use the root test. The nth root, there is no need of the absolute value. Ln n is positive for n greater than 2. N cancels with n, so I'll have n over ln n. Now the limit of n over ln n when n goes to infinity is infinity over infinity. So I need to use L'Hopital's. So I change to functions to x. The limit is infinity over infinity, so I can use L'Hopital's rule. Derivative of x is 1, derivative of ln x is 1 over x. 1 over 1 over x is just x. And when x goes to infinity, the limit is infinity. Notice something in the root test and the ratio test. It says if the limit is greater than 1 or infinity, then the series diverges. So here the limit is infinity. So by root test, series diverges. The last question, this is a series defined recursively. You remember the recursive definition of the series? We studied this in 11.1. In 11.2, the integral, the test for divergence, and 11.1, the recursive definition. This is A1, you can find A2, A3, A4 in terms of the previous term. So A2 in terms of A1, A3 in terms of A2, and so on. Well, we need to see whether the series is convergent or divergent. So which test to use? I can use here the ratio test, an plus 1 over n. And why is that? Because I can find this quantity easily, because an plus 1 is 5n plus 1 over 4n plus 3 times an. So if I divide this by an will be cancelled with an, and I'll have 5n plus 1 over 4n plus 3. And there is no need of the absolute value because everything is positive here. And the limit of 5n plus 1 over 4n plus 3, when n goes to infinity, if you take the highest power over the highest power, this would be 5 over 4, which is greater than 1. So by the ratio test, series diverges, or the series is divergent. Hope you enjoyed the ratio test and the root test.